Vertical curves are one of the most important elements in geometric design for highways. In this episode, we are going to see 1. The purpose of vertical curve. 2. Stopping sight distance. 3. Introduction about grade variations. 4. Types of vertical curve. 5. Detailed study about parabola as vertical curve. 6. Derivation of important formulas. 7. Designing a vertical curve from the derived formulas. All are within 25 minutes time, so enjoy your learning. Welcome to Civil Guru. Our videos are available in multiple languages, including English, Spanish, French, Arabic, Hindi and Tamil now. Choose your preferred language from our playlist. If you find this video helpful, hit the like button, subscribe, and share it with your friends. Thank you. Welcome. Today, we're diving into one of the most crucial elements of road design, vertical curves. Whether you're an experienced engineer or just starting out, understanding how vertical curves affect road safety and comfort is essential. So, let's take a closer look at how to calculate and design these curves, ensuring safety, precision, and efficiency at every turn. On highways, an abrupt changes in vertical alignment can create significant discomfort and even safety hazards for vehicles. Such sudden shifts in elevation may lead to accidents or vehicle damage. To prevent this, vertical curves are introduced to provide a smooth transition between two intersecting road grades. These curves ensure that vehicles experience a gradual shift in elevation rather than an abrupt change, enhancing safety, comfort, and overall roadway aesthetics. Before diving into the design aspects, let's first understand the essential elements of a vertical curve. Elements of a vertical curve. Vertical curves are defined by their grade or gradient, denoted as G, which represents the slope of the road. This is expressed in two ways. Percentage, example, 2% or 3%. Ratio, 1 in n, example, 1 in 100 or 1 in 400. Another key factor is the rate of change of grade, R, which helps determine the required curve length. This rate remains constant to ensure a uniform and smooth transition. Each country's Department of Transport establishes its own values based on local traffic conditions and road design standards. Types of vertical curves. There are two primary types of vertical curves. 1. Sag curves, used when the change in grade is positive, typically found in valleys. 2. Crest, summit, curves, used when the change in grade is negative, commonly seen on hills. While these are the two main categories, vertical curves can be further classified into 6 variations based on different grade transitions. 1. Positive grade, G1, followed by negative grade, G2. 2. Negative grade, G1, followed by positive grade, G2. 3. Positive grade, G1, followed by a higher positive grade, G2, note, G2 greater than G1. 4. Positive grade, G1, followed by a lower positive grade, G2, note, G1 greater than G2. 5. Negative grade, G1, followed by a higher negative grade, G2, note, G2 greater than G1. 6. Negative grade, G1, followed by a lower negative grade, G2, here, G1 greater than G2. Key information and elements of a vertical curve. Sight distance, a crucial factor in vertical curve design. What is sight distance, and why is it important? When a vehicle moves at a designated speed, the driver needs sufficient time to recognize any hazard on the road and react appropriately. Once the brakes are applied, the vehicle takes additional time to come to a complete stop, depending on its speed and deceleration rate. The stopping sight distance, SSD, is the minimum safe distance a vehicle should maintain to avoid collisions. In technical terms, sight distance, S, refers to the length of the roadway visible to the driver, ensuring safe stopping conditions. The SSD calculation considers three key factors. 1. Perception time, the time required for the driver to identify a hazard. 2. Reaction time, the time taken to respond after identifying the hazard. 3. Braking distance, the distance the vehicle travels after braking is applied. For example, according to the American Association of State Highway and Transportation Officials, AASHTO, a vehicle traveling at 100 km per hour requires at least 185 meters to come to a complete stop safely. Design considerations for sight distance. The driver's eye level is typically 1080 mm, 3.5 feet above the road. The minimum object height visible to the driver is 300 mm, 1 foot. If an object is not visible within the required sight distance, the vertical curve length must be increased by reducing the rate of change of grade. By ensuring an adequate stopping sight distance, we enhance road safety and driving efficiency. Derivation of important formulas. Calculating the length of a vertical curve. The length of a vertical curve, denoted as L, is determined by the algebraic difference between the two grades, divided by either rate of change of grade. The formula is: the length of the curve L equals the difference in the grades G1 and G2, divided by the rate of change of grade R, where G1 minus G2 represents the algebraic difference between the two grades in percentage. R is the rate of change of grade in percentage per chain. Standard intervals are considered as one chain. Constants used in vertical curves. Vertical curves can be designed using either circular curves or parabolic curves. However, parabolic curves are preferred because they provide a uniform rate of change of grade, ensuring a smoother transition. Recalling from mathematics, the general equation of a parabola with a vertical axis is y equals a times x squared plus b times x. The slope of the curve at any point is given by the derivative of y with respect to x equals 2 times a times x plus b. And the rate of change of grade is the second derivative of y with respect to x squared equals 2 times a equals r. Since 2 times a is a constant, it confirms that parabolic curves maintain a uniform rate of grade change, making them ideal for highway design. Tangent correction in vertical curves. What is tangent correction? In vertical curves, all distances along the curve are measured horizontally, while offsets from the tangent to the curve are measured vertically. This vertical distance, offset, between the tangent and the curve at any point is known as tangent correction, denoted as h. Let's define the setup. Consider a coordinate system where O is the beginning of the vertical curve. OA and AB represent tangents with slopes G1 and G2, respectively. The curve OB follows a parabolic profile. A point Q with the coordinates of x, y lies on the curve, with a vertical line PQR passing through it. PQ equals h represents the tangent correction, vertical offset. Here, h equals PR minus QR. Using the parabolic equation, PR equals G1x, and QR equals y. Substituting these values, h equals G1x minus y. Now we will find the value of y. By substituting the parabola equation again, y equals ax squared plus bx, and dy by dx equals 2ax plus b. At point O, the value of x equals 0. So, the slope at point O is g1. That is, dy by dx equals g1. As we know, dy by dx equals to 2ax plus b. Here, x equals to 0 means 2ax equals to 0, so dy by dx, that is g1 equals b. Now substituting g1 instead of b in general equation. Y equals ax squared plus g1x. Rearranging. Negative ax squared equals to g1x minus y. We already knew that. H equals g1x minus y. Rearranging again. H equals ax squared. Since a is a constant in vertical curve design, it is replaced with k, so h equals kx squared. Replacing x with n, that is the number of chords from point O. H equals kn squared. Thus, the tangent correction varies as the square of the horizontal distance from the point of tangency. Deriving the formula for k. To find k, we extend the tangent g1 to point C, directly above B, then draw a horizontal line CD and a vertical midpoint line FEG. The length of the chord at uniform intervals is L. The number of chords at each side of the grade is n numbers. So, the distance between the starting point of O to the midpoint of E is n into L. That is equals NL. Similarly, from the midpoint of E to the endpoint of B, also NL. So, the total length of vertical curve, L, equals 2 into NL. That is 2NL. And total number of chords in this vertical curve, that is n equals 2n. G1 and G2 equals grades of two tangents. And E1 and E2 equals corresponding rises or falls per chord length, L. Now, let us do some algebraic calculation. That is, OA equals AC. And CD equals n into E1. That is NE1. And BD equals minus n into E2. That is minus NE2. Now, CB equals CD plus DB. That is NE1 plus minus NE2. That is n into E1 minus E2. Here, at the end of the curve, CB equals to H. We already knew that H equals Kn square. Here, n equals 2n. That means Kn square equals K into 2n square. That is, for not square. Finally, CB equals for not square. That is equals to n into E1 minus E2. Now, K equals n, E1 minus E2, divided by, for n square. Here, this n and square of the n gets cancelled. So, finally, K equals E1 minus E2, divided by, for n. In the above equation, proper care for signs must be taken while substituting the numerical values of E1 and E2. Designing a vertical curve using derived formulas. In this section, we will go through the process of designing a vertical curve with practical calculations. We will cover 1. The curve length. 2. The constant value of rate of change of grade, k. 3. The tangent correction, h. Finally, the calculation of final reduced levels of the finished road surface. We will go through a sample design calculation using the tangent correction method. Given information. A parabolic vertical curve connects two uniform grades of plus 0.8% and minus 1%. The chainage and reduced level of the point of intersection are 1660 meters and 238.00 meters, respectively. The pegs will be fixed at uniform chord intervals of 20 meters chainage. The rate of change of grade is 0.005%. This means the rate of change of grade for a 20-meter chain is 0.005 multiplied by 20 meters, which equals 0.1% per chain. Step 1. Calculate the total length of the curve. We already know the formula for the length L of the curve is L equals G1 minus G2 divided by R, where G1 equals plus 0.8%. G2 equals minus 1%. Rate of change of grade per chain equals 0.1%. Thus, the length of the curve L is L equals 1.80 divided by 0.1, which equals 18 chains. Since each chain is 20 meters, the total length of the curve is 18 chains times 20 meters equals 360 meters. The length of the curve on either side of the apex is 9 chains. Thus, n equals 9 chains or 180 meters. Step 2. Fixing the tangent points. The chainage of the intersection point is 1,660 meters. So, the chainage of the first tangent point is 1,660 meters minus 180 meters, which equals 1480 meters. The chainage of the second tangent point is 1,660 meters plus 180 meters, which equals 1840 meters. Step 3. Find the reduced level, RL, values of tangent points. For the first tangent point, G1 equals 0.8%. The length of the tangent from the apex is 180 meters. The difference in elevation equals 0.8% times 180 meters, which equals 1.44 meters. The RL of tangent 1 equals the RL of the intersection point minus 1.44 meters. 236.560 meters. For the second tangent point, G2 equals minus 1%. The length of the tangent from the apex is 180 meters. The difference in elevation equals minus 1% times 180 meters, which equals minus 1.8 meters. The RL of tangent 2 equals the RL of the intersection point minus 1.8 meters. 236.2 meters. Step 4. Find the value of point E. Point E is the average of points O and B, so E equals 236.56 plus 236.2 divided by 2, which equals 236.38 meters. Step 5. Calculate the value of point F. Point F is midway between points A and E, so RL of point F equals RL of A plus RL of E divided by 2. 238 plus 236.38 divided by 2, which equals 237.19 meters. The apex value is the difference between A and F. 238 minus 237.19, which equals 0.81 meters. This value is the H value of 0.9 from the beginning of the curve. Step 6. Check calculations and calculate K. We will now calculate the value of K. To find K, we need E1 and E2. E1 equals G1 times 20 meters. 0.8 divided by 100 times 20 equals 0.16 meters. E2 equals G2 times 20 meters. Minus 1 divided by 100 times 20 equals minus 0.20 meters. Now, to calculate K. K equals E1 minus E2 divided by 4 times n. Substituting the values. K equals 0.16 minus 0.20 divided by I 4 times 9, which equals 0.01. Step 7. Calculate the value of h. The value of h at the apex point AF is h equals k times n squared. H equals 0.01 times 9 squared, which equals 0.81 meters. This is the tangent correction at the point of the apex. We can confirm this value matches our previous calculations, ensuring the accuracy of the results. Step 8. Calculate the RL values of intermediate pegs. Next, we calculate the RL values for the intermediate pegs. 1. Calculate the tangent elevation for each peg. 2. Calculate the tangent correction, h, for each peg. 3. Subtract the tangent correction from the tangent elevation to find the final reduced level on the parabolic curve. Example for intermediate pegs. Tangent elevation. Tangent elevation for the first peg. RL value of 0.0 plus the value of E1, that is, RL of first peg equals 236.56 plus 0.16, which equals 236.72 meters. Tangent elevation for the second peg. RL value of 0.0 plus the value of E1, that is, RL of first peg equals 236.56 plus 2 times 0.16, which equals 236.88 meters. Tangent elevation for the third peg. RL value of 0.0 plus the value of E1, that is, RL of first peg equals 236.56 plus 3 times 0.16, which equals 237.04 meters. Repeat the same process for all pegs until the 18th peg, that is point C. Tangent correction, that is, h. Tangent correction for the first peg. H equals 0.01 times 1 squared, which equals 0.01 meters. Tangent correction for the second peg. H equals 0.01 times 2 squared, which equals 0.04 meters. Tangent correction for the third peg. H equals 0.01 times 3 squared, which equals 0.09 meters. Repeat the same process for all pegs until the 18th peg. Final RL values. That is, elevation value minus tangent correction. Final RL for the first peg. 236.72 minus 0.01 equals 236.71 meters. Final RL for the second peg. 236.88 minus 0.04 equals 236.84 meters. Final RL for the third peg. 237.04 minus 0.09 equals 236.95 meters. Repeat the same process for all pegs until the 18th peg. For example, for the 18th peg, tangent elevation, which equals 239.44 meters. Tangent correction for the 18th peg, which equals 3.24 meters. 239.44 minus 3.24 equals 236.20 meters. This final value confirms our previous result. This is the procedure for designing a vertical curve. By using the derived formulas for curve length, rate of change of grade, tangent correction, and final reduced levels, we can ensure the accuracy and smoothness of the design. When designing vertical curves, it's not just about applying formulas, it's about ensuring that every curve supports safe transitions, handles varying grades, and integrates seamlessly with the surrounding terrain. The tools and concepts we've covered today lay the foundation for creating safer roads and a better travel experience for all. If you enjoyed this video, subscribe now and share it with your friends. Also, don't forget to press the bell button for updates. Thank you.